Okay, so how can we predict the direction in which a reaction will proceed if it's not yet at equilibrium? To do that, we're going to use what's called the reaction quotient, Q. Now, Q has the same mathematical expression as K. The difference is, so it's just products over reactants, each raised to the coefficient in a balanced chemical equation. The difference is K is the concentrations at equilibrium, and Q is at not necessarily equilibrium concentrations. Okay, so again, it has the same expression as K, except this time we're just using the initial concentrations. K is the concentrations at equilibrium. So how are we going to be able to use this? Well, we're simply going to compare the value of Q to the value of K, right? So if Q is less than K, now remember, this is products over reactants. So if Q is less than A, that means we don't have enough products yet, right? We got to make this bigger. We need more products so that Q is equal to K. So if Q is less than K, the reaction is going to proceed in the forward direction. It's going to go towards products. It's going to go towards the right until it reaches equilibrium. If Q is less than K, if Q is greater than K, so that means this is too big, right? There's too many products. So it's got to shift back towards the reactants. It's got to shift to the left. So if Q is greater than K, it's going to shift back towards the reactants. And what do you think it means if Q is equal to K?
We're in an equilibrium.
Exactly, right? So if Q equals K, you're at equilibrium. Okay, let's put this to the test. Let's try it. So let's say we have a 50-liter vessel and it contains 1 mole of N2, 3 moles of H2, and 0.5 moles of ammonia. I want to know in which direction, toward reactants or products, will the system shift to reestablish equilibrium at 400 degrees Celsius. And at 400 degrees Celsius, the equilibrium constant is 0.5. Okay, so now all we got to do is calculate, since we already have K, all we got to do is calculate Q, the reaction quotient, which again is just going to be the products raised to the coefficient divided by the reactants, again, each raised to the coefficient. Okay, we got to calculate the molarity. So 1 divided by 50 is 0.02, and 3 divided by 50 is going to be 0.06, and 0.5 divided by 50 is going to be 0.01. So now we have the equilibrium. We have the constant. These aren't necessarily the equilibrium. We have the concentrations of this reaction at this point in time. So we'll call these the initial concentrations. So we have both reactants and products in the reaction vessel to begin with. So now we're going to plug them into the QC expression. Plug it into your calculator. That gives us a Q value of 23.1. So is this reaction going to proceed towards more products, from products back to reactants, or is this thing already at equilibrium? So which way is this reaction going to proceed? Leah, what do you think?
I think it's going to go forward.
Two products. So we have Q is greater than K. Now remember, it's products over reactants. So Q is greater than K. Do we have too many or too few products?
Oh, we have too few products.
Too few products?
Yes.
Products over reactants, right? And at equilibrium, Q must equal K. But Q is too big. We have too many products.
Oh, okay.
So it's going to go back to reactants, right? So Q is greater than K. So we're going to go back towards reactants. Any questions with that? Okay, now let's talk about Le Chatelier's principle. And basically, Le Chatelier's principle in a nutshell says that anything that we do, nature tries to undo. And it really is that basic, okay? So again, Le Chatelier's principle states that when a system in chemical equilibrium is disturbed by a change in temperature, pressure, or concentration, the equilibrium is going to shift in a way to counteract that change. We can change a reactant or product concentration. So we could add more reactant and it'll go towards products. We could add more products, it'll go towards reactants. We could remove products and it'll go from reactants to products to replace them products. We'll talk about how pressure changes the equilibrium constant for gaseous reactions, sometimes, not all the time, as we'll see. And then finally, we're going to find that the temperature also will affect the equilibrium of a chemical reaction, and it depends on whether or not it is an exothermic or an endothermic reaction on how exactly it affects it. So again, let's refer back to the YouTube, right? Well, here we have our reactants, here are our products at equilibrium. Those water molecules are moving back and forth throughout the YouTube at the same rate. But again, if I remove some of the water from this end of the YouTube, we know that our equilibrium is going to be reestablished by some of this water going into this side, again, until our equilibrium is reached. So notice that we don't have the same amount of reactants and products, but that the ratio is the same, okay? So again, we could use the value of Q to calculate this, right? So again, we can see that the Q is bigger than the K value. So the Q is up here, but the K value is here, right, when it reaches equilibrium. So Q is bigger than it should be, so the reactant's going to go, the reaction is going to go from reactants to products, okay? Okay, if a reaction involves a change in the total moles of gas present, then a change in pressure will affect equilibrium. But it has to have a different number of moles of reactant gas compared to product gas. If there are the same number of moles of reactant gas as there is product gas, a change in pressure will not affect the equilibrium, okay? So again, by reducing the volume, we literally squeeze the reaction, which is going to cause a shift in the equilibrium to reduce the number of moles of gas, right? It's going to try to reduce the pressure by forcing the chemical reaction to the side that has fewer gas molecules. And vice versa, if I expanded it, if I gave it a bigger volume, right, a lower pressure, the reaction is going to shift to whichever side has more gas particles to try to reestablish that equilibrium again. Okay. So again, it's a simple step to see that reducing the pressure in a reaction vessel by increasing its volume would have the opposite effect. So I said that. Okay, so let's take an example. So here we have this cylinder, and it's filled with a mixture of carbon monoxide, hydrogen gas, methane, and water vapor. And if I squeeze this reaction vessel, right, I'm going to increase the pressure. So the only way to reduce the pressure is to go from, well, this side has 4 moles of gas. This side only has 2 moles of gas. So if I force some of these reactants to become products, I'm going to reduce the pressure a little bit. I'm not going to completely bring the pressure back to its original value, but I'm going to try to bring it back a little bit. And so it's going to shift towards more products. So now you can see I went from 2 methane molecules to 3 methane molecules, and from 2 gas molecules to 3 gas molecules. But in the end, I've gotten rid of the total number of gas molecules, right? This has 1, 2, 3, 4, 5. So it has a total of 20. But over here now I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So I went from 20 gas molecules to 18 gas molecules. So I slightly reduced the pressure, but still I reduced the pressure. Okay. Any questions with that? Okay. So When there are fewer moles of gaseous products than gaseous reactants, the equilibrium can be shifted to the right by increasing the pressure. And again, towards the reactants by decreasing the pressure. But there has to be a difference in gas molecules. If there's a greater number of gaseous products, then it's just going to be the opposite, right? So we're going to have to reduce the pressure to get it to go towards the products, and then reduce the pressure, and the reactants by. We're going to go back to the reactants by increasing the pressure. So again, it depends on whether you have more reactant molecules or gaseous molecules or more product gaseous molecules. And then again, you could just deduce which way the reaction is going to go. And again, like I said, if there's the same number of gaseous reactant molecules as there are gaseous product molecules, pressure is going to have no effect on the equilibrium, right? There's no way to change the pressure if there's the same number of gaseous molecules in reactants as there is products. Okay, then we have Le Chatelier's principle. So temperature has a significant effect on most reactions. And again, it's going to be based on whether or not they're exothermic or endothermic. So we know that the temperature always increases, right, for the rate constant. It always increases. But we're not specific of whether the forward rate constant increases more or less than the reverse rate constant. So if the forward rate constant increases greater than the reverse, that means the equilibrium would be shifted to the products. But if the reverse rate constant is increased more than the forward rate constant, that means we're going to shift it to the reactants. Well, that is directly related to whether or not the reaction is endothermic or exothermic. Okay? So we're going to be able to consider heat as being either a product in an exothermic reaction or a reactant in an endothermic reaction. Remember, exothermic, it loses heat, right? So we can think of that as a product. Now we know that it's not a real product, but we could think of it that way, and it'll allow us to determine which direction the equilibrium is going to go. So by increasing the temperature, we're going to add more product. Okay? In the case of an endothermic, we're going to add more reactants. So again, it's not really a physical entity, but we can treat it that way. So for example, let's consider the following generic exothermic reaction. So reactants are going to products, okay, and it's going to release heat. So that's an exothermic, del H is negative. So if we increase the temperature, we're increasing the amount of heat, we're increasing the amount of products, and the reaction is going to go back towards reactants. Everybody see that? So again, we increase the temperature, we're increasing the heat, we're going to go back towards reactants, which means we're going to have a smaller K value because it's products over reactants. But heat doesn't actually appear in the equilibrium constant expression, just the actual products. And since it's products over reactants, and we have less products, that means we're going to have a smaller K value. Okay? And conversely, if we have an endothermic reaction, del H is positive, we're adding heat to the system, to the chemical reaction. Well, now we're going to force reactants to products, so we're going to gain products. And now the K value is going to be larger for endothermic reactions by heating it up. So when we heat up an exothermic reaction, it goes in the reverse direction. K becomes smaller, we have less products. For an endothermic reaction, when we heat it up, we're going to drive it to more products, which means we're going to increase the value of K. Okay. Catalyst has absolutely no effect on the equilibrium of a chemical reaction. A catalyst does nothing more than to speed up how quickly we reach equilibrium. So here's an example. If you take a piece of copper and you react it with ammonia, NH3. So this is just an aqueous solution of ammonia. And as that ammonia leaves the solution and tries to escape, it passes over a copper wire. Well, when that occurs, a chemical reaction occurs. The copper acts as a catalyst, and it's just causing the ammonia to form nitrogen, molecular nitrogen gas. Okay, it's an exothermic reaction. That's why the copper begins to glow, because it's releasing a lot of heat. But again, the catalyst does not affect, it doesn't create more product. It just gets us to equilibrium quicker. That is it. So again, it's not going to affect the equilibrium concentration. It's just going to get us to equilibrium faster. Okay, any questions about that? Okay, that is it for this chapter. Sort of 1.2 times 10 to the 2 at 175. We have a 1 liter reaction vessel that initially contains 0.25 molar iodine monobromide and 0.001 moles of iodine and 0.001 moles of bromine. So in this case, we're starting off with both reactants and products in the reaction vessel. So I want to know in which direction, forward or reverse, is this reaction going to proceed at this temperature? How would I determine that? What equation, concept, idea am I going to use to solve this problem?
The reaction quotient.
The reaction quotient, right? Anytime you have this idea of predicting, right? In which direction? So it's asking you to predict something. When you're going to predict something, you're going to use Q. In fact, what you're going to do is you're going to take K versus Q. K was given to us, right? So K was already given to us in the question. It was 150. So that was already given to us in the question. What about Q? How am I going to figure out what Q is?
It's the same as the KC equation, but with the initial concentrations.
Okay, so it's a concentration of the products raised to the coefficient in the balanced chemical equation. But like you said, it's actually the initial concentrations and not the equilibrium concentrations like K. Then our products, so that's the iodine to the first, the initial concentration, and the bromine to the first. Again, the coefficients are 1, and again, the initial concentrations. So now, luckily, this is in a 1 liter reaction vessel, so that means the moles are equal to the molarity. So for the, let's see, initially contains, so there's the IBR, so that is 0.25 molar squared. The iodine was at 0.001 molar to the first, and the bromine was at 0.001 moles. So you just plug that into your calculator then, and you are going to get a value of Q then of 6250. Okay, so now how does that help me? Is it going to go to the reactants or the products? Or is it at equilibrium?
Is that going to the products because it's over 1,000?
Okay, I want you to think about this, right? Remember, these are products over reactants. If Q equals K, if it equals K, what does that tell us?
Equilibrium.
Equilibrium. Now, if I have, again, this is still products over reactants. So if this is bigger than this, do I have too many or too few products? Remember, it's products on top. It's products over reactants. So if Q is bigger than K, do I have too many or too few reactants?
You would have too few reactants? Or too
I'm
many?
sorry, I'm talking in terms of products. I'm sorry, don't think in terms of reactants. It's products over reactants. So do I have too many or too few products if Q is bigger than K?
You would have too many products.
Exactly, right? I have too many. Q is too big. Q needs to equal K. So if I have too many products, is my reaction going towards products or towards reactants?
Towards products. Towards reactants?
Yeah, right. If I have too many products, I need to go back towards reactants, right?
Oh, okay.
Does that
Yeah.
make sense?
That makes sense.
So,
Yeah.
think of it like this, right? It's always K versus Q, never Q versus K. It's always K versus Q. K needs to equal Q. So if Q is too big, I have too many products, it's got to go back to a reactant.
That
If
makes sense.
Q is small, that means I don't have enough products. I need to go that way. So in this case, it's going to go back toward reactants, or you could say what, to the left, just as long as you convey to me which direction that reaction is going.
Would that also be the reverse direction too?
You could say reverse direction. That works for me too. Okay. Any questions about that? Okay, now I want to know, what are the concentrations of the reactants and products once the reaction establishes equilibrium? How am I going to solve that? So it's asking for equilibrium concentrations. We always find equilibrium concentrations in the same way. We've already found equilibrium concentrations twice today. How did we do it?
Would you start with the ice table?
Yeah, we're going to have to set up an ice table. So anytime we're trying to find equilibrium concentrations, we're going to need the ice table. So I'm just going to rewrite the equation real quick. So we have I2 gas plus Br2 gas in equilibrium with the iodine monobromide gas. Okay, we're going to need the initial change in equilibrium. So again, since this isn't a 1 liter reaction vessel, our initial is, so the iodine monobromide, that's this guy over here, was 0.25. The iodine was 0.001, and the bromine was 0.001. So these are the molarities, right? So these are the molarities, the concentrations in terms of molarities. Okay. Caitlin, how does the iodine change? What do I put here for C, for iodine?
Negative X.
Yep, minus X, the bromine.
Minus X.
And the iodine monobromide.
Plus 2X.
Exactly, right? So again, we're going to lose our reactants, gain our products, and by in terms of X, and then multiplied by the coefficient in the balanced chemical equation. Okay, now I just add the initial and the change, so it's 0.001 minus X Same true for the bromine. And then the iodine monobromide is 0.25 plus 2x. Okay, Keenan, what's my next step?
So you would have to find x from here. I'm trying to figure out how I want to go about that. 250. So do you just do the products over the reactants?
Yeah, you're always going to use the equilibrium constant expression. So that looks like this. Okay. Then what do? Do I know the value of K?
Yes, we do. It's
It
the
was given
1
to
point.
us.
Yeah.
Right, so 150 to 2 sig figs. What about this?
That would be the 0.250 plus 2x.
Right, again, this is equilibrium. So these are equilibrium concentrations. So this will be the 0.250 plus 2x. And don't forget these coefficients. That is a very common mistake. Okay, and I'll be stressing that throughout the next several chapters. The next several chapters all involve equilibrium. And by the way, we're going to see this reaction quotient pop up in a whole bunch of future chapters, including things like electrochemistry. Okay, so that reaction quotient always allows us to predict the direction in which a reaction is going to proceed, which we're going to find out is important later on for other things as well. Okay, so now we have our iodide, which is 0.0010 minus x. And I have my bromine, which actually is the same thing, right? So I'm just going to put a squared here. Is everybody okay with that? Again, it's just this times this, which is just that squared. Okay, do I need to solve the quadratic formula? Eugenie, am I going to need to solve the quadratic formula?
Yeah,
Okay, do you see no way out of it?
you could take the root of both sides.
I didn't understand. I can't hear. There's something weird going on.
You could take the root of both sides.
Yeah, right. So if I take the square root of both sides, that's just going to get rid of those two guys, right? So then I have the square root of 150 is equal to 0.250 plus 2x over 0.001 minus x.
Can you move your paper down a little bit?
Oh, I'm sorry. Okay. The square root is, so this is going to be equal to 12.247. That was 2 sig figs, so that'll be 2. We need to bring this over now, so this will be 12.247 times 0.001 minus x is equal to 0.25 plus 2x. Okay, this is going to give me, when we multiply that by that, this is going to be 0.01, 0.03, so 0.12247 minus our 12.247x, and that is all equal to that on this side. Okay, I'm going to add this to the other side, so that's going to look like this then. Okay, and then I'm going to subtract this from both sides. So this is going to give me 14.247x, and then that's going to give me negative 0.23775. I'll divide both sides by the 14.247. And so X then is going to be equal to negative 0.016687. It actually ends up being back to 3 sig figs because of the addition and subtraction that was going on. Okay, any questions about that? So you just need to make sure that you can do this kind of stuff on your own and quickly. Okay, so now that we got X, I'm just going to substitute these values of X back in, right? So that's X, that's X, that's X. And when I do that, that's going to give me the value of 0.0177 molar for the iodine. The bromine's the same, right? So that's just going to be 0.0177 molar. And then the 0.25 plus 2 times our X value is going to give us 0.217 molar. Okay, does anybody have any questions about that? So we already established that the reaction was moving back towards reactants since Q was greater than K. And we've seen that in the negative value of the X that we determined. Again, so that negative told us that we were going back towards our reactants. We had too many products to begin with. Oops. So any questions about any of that good stuff? Okay, let's try another. So this is number 30 from chapter 15. It says a catalytic converter in automobiles oxidizes carbon monoxide to form carbon dioxide over a platinum catalyst. So carbon monoxide is produced because of a lack of available oxygen in the combustion chamber. So what happens is then it goes through the exhaust, it goes through the catalytic converter, which now has more oxygen that is taken in from the atmosphere, and it just converts the carbon monoxide to carbon dioxide at normal temperatures. Okay, carbon monoxide is a very, very stable molecule. So it doesn't just pick up oxygen and go to CO2. It has a K value that is extraordinarily, extraordinarily small. So it doesn't like to go that way. But when you use a platinum catalyst, it does go. The kinetics are very slow. The equilibrium constant's large, but the kinetics are very slow. Okay, so that's why we got to add the platinum. So first I wanted you to predict the direction in which the reaction is going to proceed when gaseous oxygen is added to the equilibrium mixture. So if I add gaseous oxygen to this reaction at equilibrium, is anything going to change? Is the concentration of the reactants and or products going to change? Is it going to proceed in the forward direction, the reverse direction, or nothing's going to happen at all? If I add oxygen. Michael, what do you think?
I'm sorry, what did you say?
If I add oxygen to the equilibrium mixture, is this reaction going to proceed towards products, towards reactants, or no change at all?
It's just going to go towards products.
Yeah, right. So if I add reactants, according to Le Chatelier's principle, anything that I do, nature's going to try to undo. So if I add reactants, it's going to try to get rid of some of those reactants by shifting their equilibrium to products. So this is going to go to products, toward products. So forward or to the right, whichever one you want, okay? Okay, it wants us to predict the direction the reaction is going to proceed when gaseous carbon dioxide is removed from the equilibrium mixture. Eugenie, which direction is the reaction going to go if I remove carbon dioxide from the equilibrium mixture?
It's going to the left.
To left, back to the reactants. So if I remove carbon dioxide, it's going to go back that way. Remember, nature's going to try to undo what I did. So if I remove this, how's nature going to replace it?
It's gonna go towards the products.
Yeah, right. So if I remove CO2, the reaction is going to shift its equilibrium and then go to more products to try to replace that CO2 that I took out. Again, if I take this out, I've changed the K value. It's now Q, right? Because it's the initial concentrations. It's got to reestablish an equilibrium to have that same K value, right? This is the law of mass transfer. Okay, that ratio always has to be the same. So if I remove CO2, again, it's going to go towards products to try to replace that CO2 that I took. Okay, Kaylee, in which direction is the reaction going to proceed if I increase the pressure? So I could do that in a bunch of ways, right? I can squeeze the volume down, or I can add an inert gas. So what's going to happen if I increase the pressure? Toward product, toward reactants, or no change at all? So again, if I increase the pressure, nature's going to want to try to reduce that pressure. Can it do it through this chemical reaction?
Are you still talking to me?
I was talking to Kaylee, but I will take anybody's response at this point.
Since there's more moles of gas on the left, would it shift to the right, or is it, since it's already in equilibrium?
No, you're absolutely right, right? To change that pressure, remember the equilibrium constant is dependent on both temperature and pressure, right? So if I increase the pressure, the only way nature can reduce the pressure is by having fewer gas molecules. So we're going to go from 3 gas molecules, and again, remember, we would only count the gas molecules if we're talking about pressure. So we will go from 3 gas molecules to 2 gas molecules. We reduced the number of gas molecules, and therefore the pressure was reduced as well. So again, this is going to go toward products. Okay, does everybody understand that? Okay, so in which direction will the reaction proceed if the reaction is heated up? Hannah, what do you think? If I heat up this reaction, which direction is it going to go?
Because the enthalpy is negative, I think that it would go towards the products.
Okay, so if we think of heat as a physical entity, it is not, but if we think of heat as a physical entity, in this exothermic reaction, would heat be a reactant or a product?
Heat would be a product.
Yeah, right. We're
No.
losing energy. So yeah, heat's going to be a product. If this were positive, we were adding energy to the chemical reaction. In an exothermic reaction, we're losing energy in the chemical reaction. So heat would be a product. So if I increase the temperature, right? So if I increase the temperature, I heat it up.
It would go towards reactants.
Right. It's going to try to get rid of that extra heat by going back towards the reactant. So in this case, it's toward reactants. Okay, any question about that? Any question about that? Again, for an exothermic process, we have a negative del H. That means heat is being released, so it would be a product. For an endothermic reaction, del H is going to be positive. That means it's gaining energy, so heat would be a reactant for an endothermic process. Okay, the last question then says, predict the direction of the reaction when the platinum catalyst is added to the reaction vessel. How is that going to change the equilibrium of reactants to products?
Isn't there no reaction? I mean, like it just increases the rate and like doesn't have any effect on the reactants or products.
Yes, let me restate that. The catalyst, all the catalyst does is speed the reaction up. It does not affect equilibrium, right? So there's going to be no shift. The only thing it's going to do is get us to equilibrium faster. It's not going to actually affect the reactants or the products.